Carbon monoxide and you!
Carry the one. Oh, sorry, I didn't see you there. Just working on a little bit of math. I'm glad you're here though, because I did want to talk to you about something. And that something is carbon monoxide. It's one carbon and one oxygen, triple bonded, just hanging out together. It's a gaseous chemical compound that you've probably heard of before. But what you may not know is that our relationship as human beings with this chemical compound began with the discovery of fire. The first mention of carbon monoxide in history is thought to have been by Aristotle, when he said, yes, that Aristotle, when he said, coal fumes lead to heavy head and death. Later on in the Byzantine Empire, which you may have learned about, Julian the Apostate and his successor Jovian are actually thought to have had carbon monoxide poisoning. In fact, Jovian actually died from the effects. Now, around the turn of the 20th century, John Scott Haldane and JBS Haldane, the JBS Haldane, abiogenesis, that guy, they actually experimented with carbon monoxide on themselves. And what they found through the exposure to carbon monoxide is that there was a measured decline in their ability to do basic arithmetic as a result of that exposure. Now, no disrespect to the Haldanes, great family, but just as a point of safety, don't science yourself. Don't do that. The CDC, which you may have heard of as well, the Center for Disease Control, actually found that over the course of 1999 to 2010, around 5,149 people actually died from accidental exposure to carbon monoxide. Now that's around 430 people per year, and that's just accidental exposure. That doesn't even take into account carbon monoxide exposure or complications as a result of smoking cigarettes. Now, we have this really long and mysterious history with this odorless and colorless and nearly imperceptible, if not for the fact that it will literally kill you, gas. But what's really going on here?
This is hemoglobin. Well, actually, this is hemoglobin. Hemoglobin is a special protein responsible for both the color of blood and the delivery of oxygen to all parts of your body. What hemoglobin does is gather up to 4 oxygen molecules at a time and bring them to different areas of need. When does your body need oxygen? All the time. And when we increase our activity by running, climbing, or playing a sport, we need an even greater amount of oxygen. At the same time, our body needs to get rid of the carbon dioxide within us, so the hemoglobin also binds to the carbon dioxide gas and carries it to the lungs for removal. With different cycles of inhaling and exhaling, the blood passes through the lungs and gets the oxygen necessary on the inhale. Then it travels to the body, delivering precious O2 to our tissues. So what happens when we inhale carbon monoxide? As we discussed, when we have as little as 1% carbon monoxide in the air we breathe, we can start to develop carbon monoxide-induced hypoxia. That's a fancy phrase for not having enough oxygen. What happens is that even though the hemoglobin does a really good job at bringing the oxygen from the air to the tissues, carbon monoxide jumps at any chance it can to ride in the red wagon, so to speak. It is a rather jealous molecule that kicks oxygen out of the wagon, the binding spot, and interrupts the oxygen delivery process. In fact, carbon monoxide binds to hemoglobin 200 times stronger than oxygen does.
Whoa. Wait. Did he just say 200 times? 200 times stronger. Well, this is oxygen. It represents oxygen at least. And this is carbon monoxide. So they look a little different. One has 2 oxygens, one has a carbon and an oxygen. But why can they both bind to hemoglobin? And why is carbon monoxide so much stronger? And if carbon monoxide is so much stronger, then why can't our tissues just use carbon monoxide instead of oxygen? The little dots positioned around the atomic symbols represent electrons. Electrons are really tiny negatively charged particles that fly around atoms at super high speed, and they're a major player in how molecules behave. Now, if we look at oxygen, O2, each individual oxygen atom has 4 electrons that are not bonding electrons. Each of the 2 lines represents 2 bonding electrons, or a bonding pair. These are the electrons that hold the 2 oxygen atoms together. Carbon monoxide, on the other hand, has 3 bonding pairs, and the oxygen and the carbon each have only 2 non-bonding electrons. Now, as we discussed, The oxygen in our blood is transported by attaching to the iron atoms in hemoglobin, and it does so using those non-bonding electrons. Inside our tissues, we use that same oxygen to carry electrons that are used in making energy in our cells. Since the oxygen in carbon monoxide has only one non-bonding pair of electrons, it can't give up or accept any more electrons for use in making cellular energy. And that's assuming that we can get the carbon monoxide unstuck from hemoglobin. Speaking of which, now we know why we need oxygen. But why is carbon monoxide so much better at binding to hemoglobin? Now, we have an idea of what hemoglobin looks like. We've seen one representation of it already. Now, this is oxyhemoglobin. This is what hemoglobin more or less looks like when it's attached to the oxygen that we need for our tissues. So if you look at the top and bottom, the shape gets kind of bent. Well, those are those non-bonding electrons repelling each other. They don't like to be near each other because similar charges repel each other. However, with carbon monoxide forming carboxyhemoglobin, the non-bonding electrons are not arranged around the atoms in a way that this repulsion occurs. So it stays straight. But there's something more important going on here. Now, you probably can't tell from the picture, but it's actually carbon that attaches to iron in carboxyhemoglobin rather than oxygen. And this new shape, the straight line between iron, carbon, and oxygen, allows for the movement of electrons between carbon and iron when the electrons form a bonding pair that ultimately creates a stronger bond between carbon and iron. The result is a bond that is over 200 times stronger than the bond between oxygen and iron. And if this happens too much, the eventual result is that cells can't make energy, which leads to apoptosis, a fancy word for the death of the cell. And if too many cells die, eventually the body dies as well from this carbon monoxide poisoning.
So, out of all the poisonous substances, poisoning as a result of carbon monoxide is one of the most common forms of death in America. And it's been a problem for all cultures since the discovery of fire. So for a really long time. Now, do yourselves a favor, go get a carbon monoxide detector, and if you don't mind, I've got to figure out how to multiply.